Greetings from GNU Linux Users Group and welcome to the second video of the series Spawn in CTF. In this video, we will familiarize ourselves with the assembly language. Assembly language is the intermediate level language to which C code is converted before converting into a binary or executable format. Before we dive into assembly language, we'll first take the time to understand what registers are. Registers in their simplest terms are internal components that store memory to be used by the CPU or processor. Registers exist in different sizes, namely 64-bit, 32-bit, 16-bit, and 8-bit. Here it is noteworthy that you will not find 64-bit registers in a 32-bit system. However, you can find 32-bit registers in a 64-bit system. Also, you might be wondering what lower bits are. Let's take an example register, AX. This 16-bit register is a combination of two 8-bit registers. AX is made up of AH and AL, which stands for A high and A low respectively. Registers are effectively classified into two groups, reserved registers and general-purpose registers. General-purpose registers are used to store temporary data within the processor, such as RDI in 64-bit, which stores the first argument to any function call. Some reserved registers include base pointer, instruction pointer, and stack pointer. Base pointer denotes as RBP in 64-bit and EBP in 32-bit is a register that stores the address to the base of the stack region in a binary during runtime. Instruction pointer, denoted as RIP in 64-bit and EIP in 32-bit, is a register that stores the address of a process that is currently executing at any point in time when the program is executing. While stack pointer, denoted as RSP in 64-bit and ESP in 32-bit, is a register that stores the address of the top of the stack region in a binary during runtime. Now that we have an idea about what registers really are, let's move to assembly. Disassembly of any function gives you its assembly code. This is what the function ret after add lead code looks like in assembly. You will notice words such as push, pop, move, add, and return. These are known as instructions in assembly language. There are three ways of writing instructions, or to be more precise, three kinds of instructions. The first denotes the type of instruction that does not require registers, for example, return. The second denotes the instruction which requires the use of one register, for example, push. The third denotes the instruction which requires two registers to be operated on, for example, add. Let's take a look at some instructions under the arithmetic category. They are meant to perform arithmetic operations such as add, subtract, or even multiply. In the first example of add instruction, 0x dead code is added to the value of RAX register, and result is stored in the RAX register. And in the second example, value of a register RDX is added to RAX, and the result is stored in RAX register. As for the subtract instruction, the first example represents that the value 0x cafe dude subtracted from the value of RBX register, and the result is stored in the RBX register. In a similar fashion, it operates on two given registers, RBX and RDX. Similarly, there also exist increment and decrement instructions. Transfer instructions are the instructions that initiate a sort of transfer of data between registers or in memory. Move instruction copies the value of destination to the source. In the first example, 0x decaf bad is copied to RAX register, while in the second example, the value of RDX is copied into RAX. Note that the value of RDX does not change during or after the move operation. The third example below is a bit different. If you ever see brackets like these, they are meant to dereference, which deals with pointers. A pointer is a value that points to a particular memory address by storing that memory address. Dereferencing a pointer means to treat a pointer like the value it points to. It stores the value located in the address stored by RDX register on RAX. Push instruction is utilized to push or add data into the stack segment of the binary, which could be referenced in the stack for further uses in the program. Pop instruction is used to pop or remove data from the stack segment of binary. Once popped, the data cannot be referenced through the stack. You will see the application of push and pop in function prologue and function epilogue respectively. Jump instructions are used for code redirection or more simply to change the flow of the program. They are also known as branching instructions. Call instruction is used to make a function call to either a library function or a user-defined function. In this example, it is calling a printf library function present in the stdio header file from the positional linkage table or PLT. Jump instruction directs the instruction pointer to the source it has in its argument. In this case, 27th instruction from the start of main. Return instructions are present generally after a function has been executed or in the function epilogue. Return instructions return the flow of control of the program to the calling function. The return instruction has several purposes in exploits such as vulnerable code redirection, shellcode deployment, and return-oriented programming. This is the assembly code of the function named ret after add lead code, whose primary objective is to return an integer after adding the hexadecimal number 0x lead code to the only argument. Here, the argument is referenced at RBP-0x4 as the fourth line indicates. The square bracket around the address means dereferencing, so the value stored at the address RBP-0x4 is the value of EDI, which is a general purpose register to store the first argument to any function. A large register, if needed, that does this work is RDI in 64-bit systems. The first three lines of the assembler dump are known as the function prologue. These three lines are always present at the start of any function. End BR64 instruction is end branch 64-bit. This instruction is used so that indirect branches go to a valid location and is used for additional safety. Push RBP saves the base pointer on the stack, and move RSP to RBP copies the value of RSP to RBP. RSP was initially pointing to the start of the function, so copying the RSP to RBP creates an independent stack for each function call. The add instruction adds 0x lead code to EAX, which initially stored the value of the argument. The last two lines are known as the function epilogue and always appear at the end of any function. Pop RBP restores the saved value of the RBP register, and return instruction returns the control of the program to the calling function. I hope this clears the basics of assembly language. We will be back with more videos. Until then, keep hacking and may the source be with you.
Back from the dead.